Very good. So our next speaker is Yury Kudryashov, and he's going to tell us about dynamics and lean and circle dynamics in particular.
Hello. First, let me list what I will be talking about. A circle in this talk is the quotient space of R modulo Z. And I will only talk about degree 1 maps from circle to itself. The simplest example is just rotation. And I will always assume that the map is monotone. And later we will define rotation number of a map like that. And I will also talk a little about monoid and group actions by maps of this type. Okay. First, so this is, I'm sorry. Okay, what I'm talking about is mostly contained in this one file, dynamics circle rotation number, translation number. And let me go back to slides. I define lift over circle degree 1 map as a map from the real line to itself with the following two properties. First, f is monotone, and second, f of x plus 1 is f of x plus 1. So if we think about it as a lift over map from the circle to itself, it means that as x makes one full turn, f of x makes one full turn as well. So this is the meaning of deg1 in the name. And the translation number of a map like this is the limit as n tends to infinity of f nth iterate of x minus x over n. And this limit always exists, and it does not depend on x. And more or less, this number answers to the following question. You have a map, it's a monotone map from the circle to itself, so the simplest example is a rotation, and now you have something which is maybe it is a rotation written in bad coordinates, or maybe it is not a rotation at all. But if it is a rotation written in bad coordinates, then it is the rotation by this number. So this is, or if we think about maps from real line to itself, then it is a shift by this number, not a rotation. By monotone, I mean if x is less than or equal to y, then f of x is less than or equal to f of y. I'm not sure what is continuum theoretic definition. So the definition in the library says monotone C to fun. So, and monotone is defined as this. The existence, okay, rotation number was defined by Poincaré, as far as I remember. And I don't remember why exactly he needed this, but it is Poincaré, more or less end of 19th century. Yeah. Okay. So here I define translation number, and if you have a map from the circle to itself, then first you lift this map to a map from the real line to itself, then compute the translation number, then go back to the circles, so take it up to an addition of an integer constant, and you get a well-defined element of R quotient Z. But just a moment. I talk about lifts of maps from S1 to S1 to maps from R to R, more or less for two reasons. First, we do not have general theory of covariant spaces, etc., in MathLib yet. And this way, I do not need to even define topological space structure on S1 or manifold structure on S1 or anything. And also, I do not need to define what is a circular monotone map, for example. And second, for many basic results, there are versions that deal with lifts to maps from R to R, and these versions provide somewhat more precise statements. And I mean, when a mathematician deals with this in a paper, of course, people very often talk about rotation numbers, but actually mean translation numbers and vice versa. People write down some inequalities on the circle, etc. We cannot do exactly this. So it's easy to just work with a map from R to R. And I made two more important decisions. One is to include only very minimalistic assumptions in the definition. So I only require that f is monotone. I do not require that it's strictly monotone, and I do not require that it is continuous. And there are two reasons for this. First, sometimes discontinuous maps or maps with steps, with horizontal steps on the graph, naturally appear, for example, as Poincaré maps of some vector field on the torus. If we go from one side of the torus to the other side, and we meet a saddle point somewhere, then it can generate a discontinuity. Okay, let me do not dive into details here. And second, just because we can. Okay, just many basic lemmas hold true in these settings, then why require more? And yes, I only work with the lifted map. When I say monotone, I mean monotonicity of the lifted map. It is possible to define rotation number of without using lifted maps. And a few years ago, I've heard a talk where the speaker defined rotation number using something called circular order. And maybe it was something like circular partial order, not linear order. So it was about something more general than just a circle. And then anyway, you can somehow define the rotation number, but okay, I only talk about lifts to the real line, and I define the usual translation number. And one trick about the definition, I did not know about this trick up until recently. For me, this trick was motivated by the paper of Etienne Gis and a hint to one of the problems in length algebra. The trick is to look at this, the sequence, not f to n, for example, of 0 over n, but f to 2 to n over 2 to n. And what is good about this sequence is that it converges exponentially fast. So when we compare an to an plus 1, if we denote this f to 2 to n by g, then we need to compare g with g squared, and it's an easy task. And you get that the distance between a sub n and a sub n plus 1 is at most, I don't remember, 2 to negative n plus or minus 1. So you have some estimate on the rate of convergence, very good estimate. And if you start with this, then the proofs of basic facts like existence of translation number or correctness of translation number becomes much easier than if you try to prove right away that the original sequence converges. Okay, And one more trick is to prove various basic estimates or inequalities for any map for any monotone map instead of a monotone map from the real line to itself. For me, the main reason for this was to reuse lemmas about one type of inequality for the reversed inequalities, because you know, if you prove a lemma about maps from R to R, then you cannot deduce just a moment. You cannot deduce a lemma with the reversed inequalities. But here in algebra.iterate home, I prove various lemmas, very basic lemmas, like, no, I'm sorry. Order iterate, yeah. Very basic lemmas, like if two maps commutes and one is monotone and another is strictly monotone, then we have some equivalence between two inequalities. Okay, and I'm going to apply this map to G equals X maps to X plus 1, and F is our circle map. But what is nice about these lemmas is that, let me open the source. Once you prove one of them, you can get the dual version in one line. Here, hf.orderDual transforms f from a monotone map from alpha to beta to a monotone map from alpha with order reversed to beta with order reversed. So it's a trick that you cannot do it if you tie your hands by proving lemmas only for real numbers. But if you generalize them, then you can easily do it. And I also made some bad decisions. First, when all you have is, I'm sorry, is this definition. And you want to speak about circle homeomorphisms. So you want to require that actually F is strictly monotone and continuous. Then you can either define another structure and transfer lemmas, and now I think that this is the right way, or do a trick. And I did a trick. I noticed that units of this monoid are exactly correspond to homeomorphisms. A map like this is invertible if and only if it is actually it represents a homeomorphism. So various facts are formulated for units of this monoid, but this is not extensible if we want to add lemmas that require, say, smoothness. Then anyway, we will need more structures. If we want to add more advanced facts, but okay. And another minor issue, I should probably I'm going to fix it in a few days, is that I defined a translation number only for circle deg1 lift. And this will not play nice with more structures. Probably I should just get these I'm sorry. Get the definition, and so this is the definition. Just a moment. Yeah. So the limit of this sequence, and probably I should just get this definition and I take it as a definition for any map from R to R. It will have nice properties only for lifts of circle degree 1 maps, but okay, we have division by 0 without error. Then
you're already using lim anyway. So you're already using the lim, LIM anyway.
Yeah.
So you're already not using the fact that it converges in the definition.
Yes.
So it won't cost anything.
Just I did not think about extensibility to other types like circle diffeomorphism, etc. when I was writing this. And okay, this waits for a very small but refactor. And okay, and probably I will find more issues when I will expand this part of the library. Okay, now what's done? First, definitions of circle of the lift of a circle degree 1 map, and the translation number. Next, some basic inequalities, like we have f of x plus 1 equals f of x plus 1, but then we need to deduce f of x plus n equals f of x plus n, where n is a natural number or n is an integer number, or the same but with x minus n or n plus x, etc., etc. And some inequalities like if you know f of 0, then you have an estimate on any f of x, f of 0 plus floor of x is less than or equal to f of x. Some very basic properties of the translation number, like semi-conjugate maps have the same translation number, or conjugate maps have the same translation number. Or okay, the original sequence f to n of x minus x over n converges to the translation number for any x. Or translation number of the pure translation is the so translation number of x maps to x plus a is a. Things like that, and some basic estimates like if you have a point that moves at least by 2 to the right, then translation number is at least 2. Next, I proved that translation number is a rational number if and only if our map has a periodic point. But since I state it for lifts to the real line, it's not a periodic point, but f to n of x equals x plus m. If you if you go back to the circle, then it will become f to n of x equals x, of course, because plus m does not change the equivalence class. And I prove exactly one non-trivial result. It's a theorem by Tianjis. It's from 1985 or 86. If a group acts on the circle, okay, since it's a group action, it acts by homeomorphisms. And you know, you fix some lift of this action to the real line, and you know translation numbers of all those lifts, then you know the action up to semi-conjugacy. So if you have 2 actions and they produce the same translation numbers, then actually these 2 actions are okay. In many important senses, they are the same. Or they're very similar to each other. So in some sense, this is some kind of a rigidity result. You cannot change an action of a group on a circle without a change in translation numbers. So I chose this theorem more or less for 2 reasons. First, it's a theorem that was published after I was born. And second, it has a rather simple proof. So it was relatively easy to formalize it. Let me show. So this is the proof, and this is the statement of the theorem. If you have a group and you have 2 monoid homomorphisms from this group to our monoid of circle degree 1 lifts of maps, and for any element of the group, the translation number, I use this notation for the translation number, the translation numbers are equal, then there exists a possibly discontinuous circle self-map that semi-conjugates one action to another. And more or less, the idea is to get f of x equals infimum or supremum of this thing. You apply f1 of g, then f2 of g inverse. And this will be a circle degree 1 self map, and it will semi-conjugate one action to another. Okay. Okay, now a couple of words about what I want to there's a typo here. Okay, about what I want to prove later. First, I want to fill in some obvious holes. Like I didn't prove that the orbits of an irrational rotation are dense. It's a trivial result, but okay. What I really want is to have formalization of something about renormalizations. And okay, it would be nice to have Hermann's theorem, but maybe it's too much. For now, Hermann's theorem says that if you have a good rotation number and your map is smooth, then it is smoothly conjugate to the corresponding rotation. Maybe, okay, and another possible direction is to prove various relatively simple results about group actions or monoid actions on the circle. For example, I don't know if you have an irrational rotation and a map with an attracting point, then not only this action is minimal, but if you perturb this action in C1, then it stays being minimal. Oh, it's just one of many results that about the names on the circle that should be easy to formalize. By easy, I mean, I don't know, maybe they should be formalizable in a week or two, or of intense coding. And yeah, I think it really would be nice to have something about renormalizations and things like that, but it may maybe it's not that easy to quickly formalize. And of course, this should be also used as an excuse to formalize various things about general dynamical systems. For example, one of my plans is to prove minimality of orbits of an irrational rotation by first formalizing Poincaré recurrence theorem. It's a bit like using microscope to deal with nails, but it's just an excuse to formalize some general theory. Anyway, okay. And there are many relatively simple facts about attractors of monoid and group actions on the circle. It seems that my time is almost over. So any questions?
Okay, well, thank you, Yury, for the talk. We're all giving you some virtual applause, some real applause. Yeah, so if you have a question, so feel free to either put something in the chat or let me know, but also you can try to unmute and just speak up.
Would you put Gish theorem back up there, please? I'd like to see that again, please. The statement of it. Oh, is that okay? I was thinking in the presentation screen.
In the presentation.
Yeah. This, yeah. Okay.
Are there significant new ingredient compared to the case of one homeomorphism, in the case where the group is the integer? Or is it only adapting the proof of one homeomorphism?
The proof is more or less the same. So in particular, I deduce the case of one homeomorphism from this theorem, just to avoid repeating myself. So basically, you just take this set for every x. You take this set and take its. I don't remember. I take supreme or infimum, but it doesn't matter. And again, as I do with other results, since okay, I prove bounded above, so probably supreme. I prove this for any order isomorphisms, something like that.
So there's also a question in the chat from Heather. Heather, do you want to ask it out loud, or do you want me to just read it out loud?
Yeah, sure. So I was asking about the method that you choose of lifting to the line. Is this also the standard way of proving these results in the mathematical literature, or do they?
Yes.
Maps on the circle.
Yes. It's actually it's hard to deal with maps on the circle without lifting them to the real line.
So in some sense, the special thing about dynamics on the circle is that the circle can be lifted to the line like that. That is what makes it tractable to study, to get these stronger results about dynamics on the circle.
Yeah, so at least while you are proving some basic lemmas, you always start with let's lift it to the real line.
Do people do this also for dynamical systems of other objects that have covering spaces? Like when people study, the dynamical systems of Riemann surfaces of higher genus, do they lift to hyperbolic space?
It's a too general question. I mean, it highly depends on what you want to prove.
Okay.
I mean, you see, here I was talking about some proofs about maps from circles itself that should somehow use the fact that they are monotone, their leaves to the real line are monotone. So you want to write some inequalities, and for these you have to leave them to the real line. But if you already have some structure, then okay, it depends on what you want.
Okay. Well, this is probably a good place to end the session and continue discussion in the social time.
I've got one more general question that is not technical at all. Can I ask it, or is it too late?
Yeah, go ahead.
I mean, the context for the people who don't know about all those people, Etienne Gis, the mathematician who proved that, is an extremely influential mathematician. He's currently the head of the French Academy of Sciences. And I'd like to ask you, did you discuss formalization a bit with Etienne? Or?
I sent him an email. He did not reply yet. I mean, I sent him an email in the end of December. I don't know. Maybe he had too many emails, or maybe.
Okay.
Okay, good. Okay, so let's thank Yury one more time. Okay,